In this section, we're going to do hypothesis testing for means when we know the standard deviation of the population, sigma. In this section, we're going to look at situations where we're testing for a population mean and the standard deviation of the population, sigma, is known. Really, it's given to us in the problem. Now, the important part of this sentence here is this part. The standard deviation of the population is what makes this symbol, the sigma, it's the fact that it came from a population is what makes it significant. If the standard deviation of the population is not known, that's when we have to use S. And whenever we use S, then we pair it up with T. So when I know the standard deviation of the population, or it's given to me in the problem very specifically, usually they're going to be very specific about either using the symbol or using the word population. If that's the case, then we're able to use the z-curve. And so therefore, the test statistic that we're going to use for our sample is a z-test statistic rather than a t-test statistic. And you'll notice we've done this before. We found the z-value before. It's simply the difference of the value we found, the mean that we've calculated, from what the mean of the population is assumed to be, which is what we have in our null hypothesis. And then we divide it by standard deviation over the square root of n, which is the standard deviation of the distribution of samples of similar size. So the steps we take in approaching a hypothesis test is we state the null and alternative hypotheses. We want to look in the problem there and hear what the assumption is about the population value. And then also for our alternative, look at what the researcher believes about that particular value, whether it's more than, greater than, greater than, less than, or just not equal to. So we're going to create those things. And then we are usually given, but as a researcher, we want to state the level of significance we want to do our test at. And then we test our hypothesis by gathering data and calculating our test statistic, finding that z-value. After we found that, then we can find the p-value of the test statistic and then compare it with the significance level. The p-value will be the area to the left or to the right of our test statistic, depending on what type of test, whether it's left-tailed, right-tailed, or two-tailed. The comparison of the p-value to the significance level tells me my conclusion. If my probability value, if my p-value is less than the significance level, we're going to reject the null. And if it's greater than the significance level, we're going to fail to reject the null. And we write out a conclusion based on that above comparison. So in this first problem, we have a computer programmer who's designed an online questionnaire she believes will take an average time of 15 minutes to complete. Suppose she samples 35 volunteers and finds that the mean time to take the test is 14 minutes. Assuming the population standard deviation is 2.5 minutes, is there sufficient evidence that the completion time of the online questionnaire differs from its intended duration? Okay, so in the last sentence there, we can really see what it is that they want us to test here. She created this test, and she believes the test to be a 15-minute test. And we want to see if it differs from what she assumed it is, of 15. So differs doesn't really give us a direction. That's just more of it could be less, it could be more scenario. It's very non-committal. So for our null hypothesis, we would just state that it's equal to 15 minutes. And the alternative would be the opposite of that, not equal to 15 minutes. Great. So we have our null and alternative hypothesis, so we know this is going to be a two-tailed test. Next thing we need to note here is that the population standard deviation was given to us as being 2.5 minutes. So 2.5 minutes is my sigma, and that tells me that this is going to be a z-test. Some other numbers that were thrown at us, there was a sample of 35, so that's my n. And when she took this sample of 35 people, she found the mean time to take the test was 15 minutes. So that is my sample statistic that I'm going to use to test the 15 minutes. And of course, our level of significance here is 0.05, so that's a 95% level of confidence, alpha equal to 0.05. So our test statistic here was 14 minutes. Let's turn that into a z-value. So we're going to compare that 14 minutes, my x bar, to the assumed mean of the population, 15. And then we'll divide that by the standard deviation, 2.5, over the square root of 35. Now, when you plug these in, if you're plugging everything in at once, it's essential that you have parentheses on the top, or you hit enter, get the result, -1. But you also have to have parentheses on the bottom fraction as well. So you want to divide the top value, the top difference, by the result of this division. So to prioritize that division before you do the main division there, which is the big bar, you've got to put parentheses around that bottom values. So plugging those into our calculator, we get -2.366. So this value that I got is more than 2 standard deviations to the left. Let's visualize this for a minute. So coming over here to my normal curve, the 15 is really at the heart of this problem. So when we're looking at the values, 15 is the assumed value, and then we're going to compare it to the z's underneath it. So we got 14 as a result, right? We know that's on the left. I don't really know how far it is until I've calculated z, but here's what I ended up getting. So it's a little more than 2 standard deviations to the left. And because this is a two-tailed test, the p-value is going to be the area to the left of this, but then it's also going to be the area to the right of its positive counterpart, positive 2.366. The definition of p-value says that it's the value of the p-value is the probability we'd have gotten the result that we did, which is 14 minutes, or something more extreme, so that would be going to the left. But then we also have the extreme area in a two-tailed test is also on the right-hand side. So the p-value is going to be the sum of these two areas. This one and that one. Now, we could find one of them and then double it. You can also go 1 minus normal CDF. We're using normal CDF because we're on the z curve here. And go -2.366 to positive 2.366. So in other words, we're finding the area in between and then subtracting it from 1. And then comma 0, comma 1, because we are on the z curve, and that is what the z center value is. The mean on the z curve is 0. So I'm putting these numbers here just so that we can see the relationship of these. Plugging these into our calculators, we end up getting 0.0180, because we get 798, and so that that 9 gets rounded up because of the 8, which rounds up the third number there, the 7, to a 8. All right, so that is my p-value. The p-value is 0.0180. Now, if you just found one of the tails and then doubled it, that's what you should get as well. Now, the p-value in this case is less than 0.05. This is my sigma not sigma, my alpha, and then this is my p-value. In other words, what we've seen here is that the probability of this outcome, if we assumed the true number of minutes it would take to complete this test was 15, we would only see this type of deviation from that only 1.8% of the time. That is a very low probability. And so what we assume then is that because of the low probability, it's more likely that the true population mean is not 15 minutes as we assumed. Otherwise, why did it only take an average time with 35 people? Why did that average time come out to be so much further to the left, 14 minutes, than our assumed 15 minutes in this case? So, this provides strong evidence against the null hypothesis. If our if our p-value is less than my alpha, then we are going to reject the null. So my decision here is to reject the null. And then we're using our template here. We say reject the null. There is sufficient evidence that the average time to take the test is different than 15 minutes. So you'll see this part here, when I said there's sufficient evidence, I'm just basically restating what the alternative hypothesis is saying, right? That the mean time, and we're putting in context of this problem, the mean time to take the test is different than the assumed 15 minutes. That is stating the alternative hypothesis. Let's take a look at another example. Here, Wikipedia is an online free encyclopedia, reports that in 2006, the average American woman is 25 years of age at her first marriage. A researcher claims that for women in California, this estimate is too low. Surveying 213 newlywed women in California gave a mean of 25.4 years. We also assume the population standard deviation is 2.3 years. Using a 95% confidence level, determine if the data supports the researcher's claim. All right, so again, I want to point out here in the wording of this problem, we're told the population standard deviation is 2.3 years. That is a sigma, because it came from a population. And this is going to allow us to use z then. Our result from our sample was a mean of 25.4 years. And so that is my x bar. And our alpha in this case is going to be 0.05 again. 95% confidence means a 5% significance. Now, what's being disputed here is the average age for American women, and we're specifically looking at women in California. Now, it's just assumed that it's 25. According to the Wikipedia, this is for women in America in general. And what we're saying is, all right, let's look at women in California and see if they have the same average age. The claim by the researcher is that this estimate of 25 years is too low. And so he or she believes that it's greater than 25. There's different ways that we do this, but I like to always make the null about equaling something, because really that's what it's kind of all about. 25 is my assumed center, because we're really arguing about where is it centered. And the alternative is always arguing one way or another, to the left, to the right, or just not equal to. And so here I'm going to put the x below, but above it I've got the z. Now, our result did get something that was above that. It was 25.4. And so I'm going to put that over here on the right. Now, I don't know how far to the right that really is. It could be a lot closer. But when we find our test statistic value, our z, That'll give us an idea of how far to the right I really am. So now we determine the test statistic. I got my random sample, 25.4 was the result of that. We're going to divide that by the standard deviation 2.3 over the square root of my sample size, which was 213 women. Again, you want to put parentheses if you're putting this all in at once, but you have to put parentheses for that bottom. That's essential. Carrying this out, plugging this into your calculator, we get 2.538. Positive as we assumed, because we know it's higher than 25. And so it's the right sign. And we see that it is pretty far to the right. In this case, this is a right-tailed test because of my alternative hypothesis being greater than. And so the p-value is simply just going to be the area in that one tail. And so we'll use normal CDF to find that. I'm going to take 2.538, go to something really big like 1,000, comma 0, comma 1. And that gives us 0.0056. So the area to the right is 0.0056, meaning that there's a 0.56% probability that if the mean age was really 25, that I would sample 213 women in California and get something that is 0.4 years above that. So there's a very low probability of accidentally getting this kind of result, right? Even though that, the true age in California of women is the same, 25 is what I'm saying. So there's very little probability that it was just my sample that made the difference. But if I were to take another sample, it might, not put me so far. So that's a very low probability. My alpha is 0.05, and this is less than 0.05. So we have 0.0056, my p-value less than 0.05. This tells me I'm going to, again, with strong conviction, reject the null. Reject the null, there is sufficient evidence to suggest that the mean age of marriage for women in California is greater than or more than 25. Let's look at one final example here. A recent study showed the average number of children in Europe is 1.48. A global watch group claims that German women have an average fertility rate which is different from the rest of Europe. To test their claim, they surveyed 128 German women and found they had an average fertility rate of 1.39 children. Assuming a population standard deviation of 0.84, does this data support the claim made by the Global Watch Group at a 90% level of confidence? Okay, so the question here is about the average or the fertility rate in Germany. And we have, first of all, the main question here, the number that's being questioned is this 1.48, this average of 1.48 children. And the belief by the researcher stated here is that it's different from the rest of Europe, that the German women's birth rate, fertility rate is different than the rest of Europe. That's, again, very non-committal. So we're going with a 1.48, not equal to, for our alternative. I do want to point out the population standard deviation here is given to us. So we know that sigma is equal to 0.84, and this tells me I am using a z. So this curve here is a z curve, a standard normal curve. So to test their claim, they've surveyed 128 German women. That's our n. So n is equal to 128. And the result of that test was that it appears to be less than the assumed population value. So X bar is 1.39. The alpha level that we're using with a 90% confidence level, that means alpha is at a 10%. Right, so looking at this from a Z standpoint, 1.48, we could see would be our middle assumption. And what we got was something less than that. We got 1.39. And so what we want to figure out is what is the Z value that would be associated with that amount. We assume it's going to be negative because if we take 1.39 and subtract 1.48, of course that's going to give us something negative. Our standard deviation was 0.84, and the size of my sample was 128. Plugging these in using parentheses on the bottom and top values, we get a Z value of negative 1.282. Or I'm sorry, 212. Now that actually would put us a little closer to zero there. So I'm going to adjust that. There we go. That's better. And because it's a two-tailed test, because of our not equal to in the alternative hypothesis, my area is going to be to the left of negative 1.282, but then also to the right of 1.212. I keep on saying 82. I don't know why I keep doing that. And the area to the right over here. So the p-value is going to be the sum of those two areas. And so we'll go with 1 minus normal CDF, and we will write in the two boundaries and just subtract that from 1. And it should come out to 0.2255. So the sum of those two areas, 2255, this is greater than my significance level of 10%. That tells me this is not strong evidence. My value did not fall far enough away from where we would expect it to, which is around 1.48. It wasn't extreme enough in order to disprove our assumption that the fertility rate is actually 1.48. It just wasn't different enough, and so we failed to reject the null hypothesis in this case. We then go on to say, so we either reject or fail to reject the null. We say there is insufficient evidence. So now we always talk about the evidence, right? The evidence is either supports or does not support the alternative. In this case, it's insufficient evidence that the fertility rate in Germany is different than the rest of Europe, which is 1.48. And that is our conclusion, not only of this particular test, but this video lecture.